So how are X-rays generated? Well, you need an X-ray tube like this one. Okay, so you see this is the standard X-ray tube, and it comprises of two circuits. One with a very low voltage, okay, which is this one here, and one with a very high voltage, which is across the whole of the tube there, okay. The first circuit has a low voltage connected to tungsten wire, which allows temperatures to increase and reach really, really high levels. At these very high temperatures, the electrons are so excited, it's really, really easy to just pull them off. This is called thermionic emission, as in thermal energy. What pulls these electrons off, though? You do need something to attract them. Well, that's what this other big circuit is for. Now, these can go up to 25,000 volts or even higher, depending on some sources. But they connect up to the anode here. So this is a strongly positive anode. And what the anode will do to the electrons that are accumulating loosely here, they basically attract and pull off the electrons so that they stream across. Now they stream across accelerated. Okay, they go up to very, very high speeds. And when they get to the anode here, they start to collide with the atoms inside this material, and due to those collisions, they decelerate. Now, what has that got to do with X-rays and generating X-rays? Well, it's to do with this fact here. Oops, going the wrong way. Okay. Whenever charges accelerate or decelerate, electromagnetic radiation is emitted. So when the electrons go from really, really fast to much slower here, that drop in velocity emits a photon of energy through here, okay, the X-ray window. It's explained in the text in a little bit more detail, okay, as it says on here. When an electron interacts with one or more atoms in the metal anode, it decelerates and emits one or more X-ray photons. These pass out of the transparent window. Okay, so to sum up, we have a low voltage with tungsten wire, and through thermionic emission, the electrons are pulled off and accelerated by a high voltage anode. And then inside the anode, the electrons are decelerated via collisions with the target, call it the target atoms. Because they decelerate, they emit photons of X-ray electromagnetic radiation. Now let's have a look at the entire spectrum of X-ray photon energy that can be given off. If you remember, a photon size can be calculated from h, which is Planck's constant, times frequency. Frequency is inversely proportional to wavelength. So in this graph, what you're seeing is that there is a minimum wavelength, which equates to actually a maximum frequency. And then after that, there's a whole range. Now, why do we get these different types of wavelength? Well, it depends on the electron's interaction with the target material. So if you imagine an electron that has loads of kinetic energy, half mv squared, and it collides with an atom, in that collision, some of that kinetic energy goes to the target material. It excites the electrons in the target material, and some is given off as a photon. Now, this collision can be very, well, there's a whole range of different kinds of collisions. It could be a head-on collision, it could be just skitting off the sides. So you basically have a maximum situation when all of this kinetic energy, all of it, is given off as HF. So imagine the electron collides with the target material And as it does that, it actually doesn't give any of its kinetic energy to the particle. It actually emits all of it as a photon HF. Now that maximum situation would be on here. And every single other point on this graph is basically an amount of photon energy that's given during the collision, which has its range. And there's a maximum somewhere in the middle, and then it peters down. So this tells you what the range of different X-ray wavelengths can be given off by the electron as it comes close to the target material. It does actually get a little bit more complicated than that. We have this curve here, which tells us all the different wavelengths that an electron will possibly give as it collides with the target material. But then you also get these little peaks. What are they all about? Well, the atom, so if we think about the target material, it has electrons as well. So what tends to happen is that when the electron comes close, so we draw this electron comes close, and it gives some of its kinetic energy to the electrons it interacts with. So you can imagine this highly negative electron zooming through here, okay, maybe skitting off the sides like that. The electron will get excited, will leap up a couple of levels, and then comes straight back down. When this happens, and we've looked at this in energy levels, and we'll look at that in a second again, when it comes back down to its original orbital, it gives off a photon. And that photon is also inside the X-ray range. So what happens is your electron gives off all of these different wavelengths of X-rays as it goes through the atom. However, it then excites the electrons inside the atom. They get excited, they jump up, and then when they come down, they give off some electromagnetic radiation as well. And these peaks correspond to those photons of energy. Okay, and why do they happen? Well, if we look at an energy level diagram here, an incident electron excites electron in the atom to a higher energy level, so it goes up, bling, and then when it comes back down, an X-ray photon is emitted. Now these peaks that we see, these peaks, always fall in the same place. They correspond specifically to different wavelengths, and these wavelengths correspond to energy levels. So you would never get an energy level, for example, you'll never get a photon which is between one energy level and another. It will always be from one to another. So you will get discrete photon packets that correspond to energy levels which correspond to these positions or the position of these spikes. So to sum up, X-rays are given off through the action of the electron as it moves through the target material. As this electron decelerates, it gives off photons of X-rays. In addition, the target material electrons get excited and they give off some X-ray radiation, which also adds to this spectrum array. Okay, so now let's try and look at some calculations. If we consider the kinetic energy of an electronic charge, half mv squared, well, the first thing to remember, this is a bit of review, is that a charge in a field has kinetic energy equal to EV, E being the charge, which is the electron charge, times the voltage. Okay, so calculating or finding EV, whatever the voltage is on the plates, will give us the kinetic energy. Okay, so if now we go back to our spectrum graph, you remember there was that minimum wavelength. That minimum wavelength corresponds to the maximum frequency possible. And that maximum frequency would occur if this crazy electron that's zooming by gives all of its kinetic energy away as a photon. Okay, so in that situation, we would have EV, which would be the entire amount of kinetic energy available, would be equal to HF, the size of the photon emitted. But frequency is the speed of light over the wavelength. So if we put these two together, we would have EV equals hc over lambda, which gives us our formula, or relationship, which rearranging would give us lambda minimum. Okay, because remember we started with the maximum frequency. Yep, so now we're going to look at the minimum wavelength, which is the same, equals hc over EV. So we have Planck's constant, again this is in your data booklet, c, which is the speed of light, E, which is the electronic charge, which is also in the data booklet, and V, the potential difference that is accelerating the electron, which will be a very high value.